everyone gets given the opportunity for a master's. I mean, I'm not. No one in your family will. You know, and I'm just like, yeah, but Mum, it's just another year. You know, and I really don't think I've got it in me.
I'll do an extra 5 years. Just don't let me go. I don't want to go to work.
So,
sorry,
let's go. Okay, so the class equation. And the two proofs we're going to do today.
Yeah.
Use the class equation. G is a group, finite group. Where A are references of the conjugacy classes. So the element conjugation by various elements of the G. So we let x1 up to xk be a set of representatives, one from each congruency class, but only of the multi-element ones. Okay, because some conjugacy classes are special, they consist of one element. For instance, the identity is always in its own conjugacy class. The identity is only conjugate to itself. Okay, so when you conjugate it by anything else, G, E, G inverse, it's always equal to the identity. Next. Presumed conjugate xi is the centralizer of xi. That's equal to the set of g's in G. This is basically the stabilizer. The xg inverse equals x. The stabilizer of x. Or stick an I there. I. Stabilizer of xi. Except when we're talking about the action by conjugation, we call the stabilizer the centralizer.
Z is the center.
Z is the center. Yeah.
Right, that's not confusing.
Z, the German word Zentrum, center of G. So this is gathering together all the elements of G, which are in their own conjugacy classes. For all G and G, G inverse X, or alternatively, that's the same as saying Gx equals Xg. It's the set of all the elements X that happen to commute with every other element of G. Okay. Okay, so let's go for Cauchy's theorem. All right, is that okay? Everybody happy with the statement, or with the class equation? Oh, and I should say, each of these things, one of the theorem, whatever it was called, but so this is the index of Cx1 or Cxi in general in G, the number of cosets of that. It's the number of elements in the conjugacy class.
Yeah.
Yeah. But it's just a simple quotient.
G over
C
xi.
Yeah. Or size of G over size of Cxi. Yeah. Etc. Top for the other ones. So we're basically going to, the two theorems are theorems about the existence of certain subgroups in G, and it's all arguing about primes or powers of primes that divide G. And the class equation is a nice device for that, because we've got the sides of G on this side, got a bunch of various quotients of the size of G here, ratios, size of G over the size of a certain subgroup, and you've got a size of a certain subgroup of G.
Wasn't that the whole group? Wasn't that defines ZG? the centralizer, the stabilizer, was the size of it.
Say that again.
But that Z of G was like a big segment of it.
Okay.
Like almost the
The centre's just those ones with dots one.
All of those ones in the singleton set is a set with one element. All of those single element ones, where you gather all those elements together, they are all contained in the center.
they're all contained.
They are all of the elements in the center.
Right.
Each element from the center in that diagram of the partition, each element in the center is sitting in its own conjugacy class.
Yeah. This is only one element in there. Right.
Because for these elements X that are, when you conjugate them by in fact X itself.
Yeah.
So where does X orbit around? Nowhere.
No,
Just stays at itself.
Yeah.
It's always stuck at itself
Right.
under the operation of conjugation.
So we're at the start of chapter 15, Steve. Did you watch yesterday's
Yeah, I
lecture?
watched it last night.
Okay, good. So we're picking up from this class equation and we're about to go into proof of Cauchy's. So any other queries about the class equation? Okay.
What is it used to? What would you use that to find?
Well, we're about to see it. Like we're about to make it work, make it earnest, keep it. Okay. So this is the answer. So perfect question to lead us into. What use is this? Yeah. Basically. Well, let's see. So G is a finite group. So we can think of the class equation for G. And P of prime number such that divides the order of G. And the conclusion is G has a subgroup of order P. G, or alternatively, like that, any element of order P will generate a cyclic subgroup of order P. And indeed, in a subgroup of order P, every non-identity element within that subgroup has order P. So Lagrange's theorem allows subgroups of order P. This point we're going in the opposite direction to Lagrange's theorem. So Lagrange's theorem would not complain about a subgroup of order P. Lagrange's theorem says the size of the subgroup has to be a divisor of the size of the group. Okay. But now we're going in the other direction. We're saying, okay, suppose here's a nice divisor of the order of the group. Is there a subgroup of that size? Okay. So it's going in the other direction. Now proof is, okay, we're trying to prove something quite strong. We're trying to prove something about every finite group. Every has some prime numbers, at least one, that divides into its size. Yeah. So it's quite a strong statement. All right. So it's not going to be a one or two liner. Just that, you couldn't hope to prove something about all groups necessarily in one or two lines. So you need some systematic way to step through the groups. And how can you organize an attack on all groups? Well, maybe one of the first ways to think of it is, well, let's take them all in order of their size. Okay? Let's deal with small groups first, and move on to bigger groups. So that suggests the idea of induction. Okay? So we will use induction on the size of G. Okay? So what's the base case going to be? What's the beginning case? Now, when we've done the introduction to induction, again, and the base case is always n equals 1. But what's the base case here? Not equals 1. I mean, what's the smallest that the size of G can be to be
an example for the application of this theorem?
3.
2 is right. Yeah, the smallest thing that has a prime dividing. Yeah, that's true. Except we'll keep it general. We don't want to start specifically arguing about 2, do we? Because then we'll have to specifically argue about 3. So we want to keep that point of general. So we'll keep P being general. So the smallest G can be his size. Just say 2, but say it in a general way.
Oh,
P.
Yeah.
Yeah. Yeah. So that's the base case for this argument. Yeah. So the prime itself is a subgroup of G of order P. Base cases are normally trivial. The answer is normally just staring you in the face. What's the subgroup of size P of G? Group itself. G is a subgroup of size P. It's the group itself, but it's a subgroup of order. So the base case is true, trivially true. Yeah. So we now assume, so that's the base case done. Now it's going to be strong induction. So we assume the theorem holds. Assume the theorem holds for all groups of size strictly less than the order of G. Now we're going to try and prove it for a general G. So we're going to try and show that assuming it holds for all groups of smaller size, it holds for a certain group. That's the induction step, going from the truth of the thing for small sizes, implying the truth of something bigger. Okay? Because it's true at the bottom, it will therefore be true for all groups. Okay. So, so we think of the class equation. I'm not going to rewrite it out again. I'll just literally write that top line out again. Okay. So we consider the class equation of G. So the argument splits into 2 cases. Case 1 is the easier case. So we want to tackle G with reference to the objects described in the class equation. So the simplest case, now you see there's various subgroups referenced here. G in the class equation for G is the center and these centralizers. Okay. So the simplest case would be, suppose P divides the size of one of the centralizers, or one of the I's. How should we argue that? So we're supposing that one of these centralizers, which are subgroups of G, that they are divisible by P.
The size of the
Indeed. Perfect. Well, we are done. See, this is covered by the induction hypothesis that we've just gone to the trouble of assuming. Cx of I is a proper subgroup of G. So it's smaller than G, this size smaller than G. We probably need an extra assumption that G, because, okay, so you might worry, well, maybe the centralizer could be all of G. Well, if the centralizer is all of G, basically means that everything centralizes an element. Well, then it will be in the center. So if everything is in the center, the group G is abelian.
I think strictly speaking, we need a extra condition deal where we're not in the non. And then the class equation would just simply be this.
G is the size of the center. The center will be all of G. And we've already done all these theorems for abelian groups because we had our fundamental theorem of finite abelian groups a couple of chapters ago. So we are dealing with non-abelian groups. So there are some of these xi's around to argue about. So if P divides the order of one of them, we notice that that's a smaller subgroup. Okay? So by assumption, CXI has a subgroup of order P. Some subgroup, call it some H of order P. And H is the required subgroup of G. Because if H is a subgroup of the centralizer is a subgroup of G, so H must be a subgroup of G under this size. Okay? So that's the easy case, so to speak. Okay? When in fact G contains something that we've just assumed, we've assumed the truth of the theorem before. So we have to worry about, so that's fine, we proved it in that case. So now we have to think, well, what if that's not true? Okay. So case 2 is the everything else apart from case 1. So for case 2, we're assuming for all I, P does not divide the size of C of xi. Yeah. P divides none of the orders of the centralizers. Well, is everybody clear on that? That's case 2. So it's the complement of case 1. Everything apart from case 1. Well, let's look at our class equation again. Okay, case 2 there. So there's the class equation. Now, P, remember, is a prime number that's dividing G. So now we've assumed that P does not divide any of the sizes of the centralizers. What can we say about P and these integers here? So these integers here are all these ratios where you take the size of G and you divide out by the size of one of the subgroups, which the size of one of the subgroups is some kind of divisor of G. But if P, we're essentially saying P does not divide any of the denominators here.
But it does divide the top.
But it does divide the top, so what can you say?
You got a whole bunch of ratios here. The numerators are all divisible by P, but P does not divide any of the denominators. So the point is, P still divides this whole integer. It divides order G, and we've divided by the order G by something, but we haven't divided by P, because we're assuming now P does not divide any of these. It's still a factor. There's still the factor P up here. It hasn't been cancelled out. We've maybe cancelled out some other factors, but not P. So that fraction is that integer is divisible by P. So is this one, so is this one, so is this one, so is this one. All these terms are divisible by P. Anything else in the class equation we know is divisible by P?
Will be centralized. Or will the G itself?
The G itself, yeah, because that's in the statement of the theorem. We're assuming P is one of the divisors of this. So what's the conclusion we draw? P divides this thing. P divides all of these. Therefore,
It must divide the
it must divide the size of the center. Because you can just put all these integers, just send them to the other side, minus signs. And then the left-hand side is something divisible by P, minus or plus, plus a load of things that are also divisible by P. So you can factor P out of everything. Yeah, so P must divide the size of the center.
So for all P does not divide the CXI, So P does divide the order of G divided out by the order of CXI. So from the class equation, we get that P divides the size of the center. And if we are, what can we say here? In the earlier chapter, the fundamental theorem of finite abelian groups, we classified abelian groups. Abelian groups are isomorphic to direct products of cyclic subgroups of various prime power sizes. So you can easily pick out a subgroup of size P. Okay, we're also covered by the induction hypothesis, because since I added in, I have to think about, but for the sake of it, for the sake of argument, I've added in the assumption that G is non-abelian. So the center is a strictly smaller part of G. Can't be all of G, because then G would be abelian. And the center is all those elements that commute with everything else. So if it was all of G, that means everything commutes with everything, so it means it would be abelian. So if we're assuming G is non-abelian, there is some non-commutative stuff going on. So the center can only be a smaller part of G. So the center is a subgroup of G, but it's strictly smaller than the size of G, so it's covered by the induction assumption. And the size of the center is strictly less than the size of G, that's G non-abelian. So center of G has a subgroup of size B by assumption. And this is also a subgroup of G. It's also a subgroup of G. But this is the subgroup of size P. This is also a subgroup of G. So G does have a subgroup of size P. And case 1 and case 2 are exhaustive. Yeah. Case 2 is the negation of case 1. So we proved it in all cases. Yeah. So just NB cases 1 and 2 are exhaustive, meaning, every possible world is contained in one of those cases. So therefore, we've successfully achieved the induction set. Assumed it was true for smaller subgroups, for smaller groups than G, therefore it's true for G. So true for G of all sizes by induction. Okay. Quite a nice, elegant argument. Nice proof by induction being used. Good example of how you proceed in arguments by, splitting into cases like this. In effect, so like we had this problem of, okay, so we assumed it's true for smaller groups. How do we prove it for G? Well, the thinking goes that, it might be easy to prove for G if it's true for one of the subgroups of G. So yeah, it could be true like that. Of course, we don't know if that's true or not. But at least this allows you to separate off a case. If it was nice, it would be true. But then that immediately gives you something else. You say, well, what if it was not nice? But then you get an extra assumption, you see. You're dealing with the not nice cases in a way. So you've got more information. And this although this looks kind of negative, P does not divide that, okay? But when you examine the class equation, it turns into something positive. Okay, P does not divide that, but then suddenly that implies, P divides all that stuff. It also divides this, so you get more, you get conclusion. P must divide this. And then you can proceed in argument. So it's a good example of when you're in the middle of arguments, you in effect, by splitting up and analyzing different cases,
You deal with easy cases, but then the hard cases, you kind of have extra information. The fact that they're hard, you know, that maybe gives you more information to build your argument.
Okay. So straight away we can go into, yeah, or let's have a look at an example. Or well, he does an easy corollary from that. Corollary from that says if G is a P group, remember G being a P group means every element has order some power of P. If and only if now we know if the size of G is itself the power of P. Okay. Because if the size of G was not a power of P, that means there was another prime that divided it, another Q. If there was another Q that divided the size of G, then G would have to contain elements of order Q. It would have a subgroup of size Q. So a subgroup of prime size Q has elements of order Q within it.
It mentions there in case 2 that since Z of G is abelian, but we've assumed that it's not abelian.
No, ZG is abelian.
It has to be
The
abelian
subgroup of the centre has to be abelian
because it's the whole thing.
because it's the section of G that is commutative with everything.
Everything. All right. Yeah.
So we assume G was non-abelian.
The very first thing.
The whole group is, the group is non-abelian, right? But that doesn't prevent some of its elements being commutative with everything.
Right.
And those make up the center.
Yeah.
Right? If the center happened to be all of G, then G is in effect abelian.
Mm.
Yeah. But so you can have a non-abelian group, but that doesn't mean nothing commutes with anything.
Mm.
It just means there are examples of non-commutative stuff going on with them.
Right.
So it could have a portion of the group, a subgroup of it called the center, which consists of elements that do commute with everything.
Right.
Yeah.
Okay.
So that doesn't conflict with it.
That's yeah.
Yeah.
Just it felt like there was some sort of conflict.
So it's the good, if you call being abelian good, non-abelian bad, the center is the good part of the bad group. Yeah. And it's always at least the identity is good.
I thought you were going to say the ugly.
Beautiful, ugly.
Do you think that's a proof why the centre is a subgroup?
Yeah, indeed.
I'm just forgetting it. Like, I think it's probably quite trivial.
I think it does come out immediately. So ZG, which, you know, here you get it as it's a subset, of course. So this is for all G and G. Okay, so it's clearly a subset. So the proof of this is a subgroup.
Yeah, it's quite, yeah.
So certainly the E is in the center.
Yeah.
Yeah. EX is equal to XE. Both equal to X. Product of things. So if X and Y are in the center, XY, is that in the center? Oh, sorry. Yeah, so you have to think about multiplying G on the left of XY. What can you do? Ultimately, we want to show that this is equal to XYG. Because that will show that the product is in the center. Everything commutes with it.
GX itself equals to XG.
Yeah. Because X is in the center. And you can say,
oh, in Y, so
It's also
in the centre, yeah. So yeah.
let's say it's a bit like that, yeah. So that implies XY is in the center. So it's closed under multiplication. And then the only thing you have to do is X inverse. So GX inverse. Don't you worry about that. We want to show that that's X inverse G
Well, because X.
for any G.
If X exists in the centre, doesn't its inverse also exist in the centre?
Well, that's exactly what we're trying to prove here.
Right.
But that's just the one that was on the
You're prejudging it.
Ah.
Yeah. So you're right, but that's
There's
the
an added
task
step.
here.
Yeah.
That's the task here.
Well, Isn't there a G inverse? No, that wouldn't help.
G is an element of.
Remember, the commutativity holds for every G. For every G, it is true that G of X is XG. Now you're somewhat hampered here because we don't have X here, we got X inverse.
But can't you, instead of proving that, can't you just prove it's kind of positive?
Yeah, you could.
Or then you just turn it round.
Or there's a neater kind of twist you could do.
Isn't it just that top assumption GX is equal to X of G? So wouldn't by assumption that G inverse?
No, because that's what we're trying to get.
No,
That's what we're trying to
prove
get.
it. We don't know. What we don't know is that X inverse is necessarily in the center.
Sensor.
Yeah,
Right.
but what can you do with that top condition? So we do know GX is XG. So what can we say? Well, we could take the inverse of both sides of that. The inverse of both sides with that would be equivalent to saying the inverse of the left is X inverse G inverse. The inverse of the right is G inverse X inverse. Now that doesn't quite get you what you want because we want X, we want G. Well, you see, this is true for every G. So we could just look at the version of this equation for G inverse. So we can say G inverse X equals X G inverse. And then when we take the inverse of both sides, we'll get what we want here. Or in effect, the same thing, there's a kind of a trick.
Jesus. So that
Yeah.
flips it, makes
So-
G inverse and then X.
Any element is
Yeah.
equal to the inverse of its inverse.
Oh my god.
And then, so you can leave the outer inverse alone, but apply this middle inverse. And it will say that's equal to XG inverse.
And then flip it again.
Not yet.
Oh no.
Then use the fact that X is in the center.
Oh, so you can move it
So
then.
you can move it, so you can make that G inverse X,
It's still the inverse
still
of the
that
outside.
inverse, and then apply that later inverse.
Bloody
You get
hell.
X inverse G. But that is in effect just the same thing as choosing that equation for the element G inverse, which is the inverse of this G, which I'm trying to prove from down here. So that's the proof. It's got the identity, it's closed, and it's got inverses. So it is a subgroup. That's just a bit of trickery. It's more natural, I think, to start from know that G inverse X is XG inverse.
Just center elements, they commute with everything.
Yes. Yeah. And it's always always true of the identity of this. So every group has a center. It might be small, might just be the trivial subgroup, or there might be some more interesting stuff. And yeah, typically even bad people have a little bit of good one. So a typical case would be a non-trivial center. Yeah. You have to be awfully bad to have only the tiniest bit of
I have to picture matrices when I think of commutativity.
Matrices are a good example because they're non-commutative.
Because I think of like, I'd make 2 by 2 that's just all the same. 2, 2,
Yeah,
2.
like some matrices commute.
Yeah, that's. the
So
other
what's a
way.
matrix that commutes with every other matrix?
The identity.
Yeah, something
Something
more interesting than
Something
the
where all
identity.
the elements are the same.
Like you just said them 2, 2, 2, 2.
No, that wouldn't.
There's only a
Diagonal
diagonal.
matrices.
Oh, where it's
Just
So
Oh.
diagonal matrices. So
again, they're basically the equivalent of doing just a linear vector.
So I can multiply that by any 3 by 3 matrix, and it'll be the same as the same matrix by the ABC.
Surely if they're all the same, they'll be. Because you're multiplying by the same
Probably as well.
number. It
Yeah, I
doesn't
think
matter which direction
probably.
it goes. Numerically speaking.
Oh no, it won't.
Right.
Try a few examples.
Okay.
Because if they're all the same, then the first entry in the product, so if it's all ones, right? First entry in the product, the top left entry in the product will be the sum of the first column. But if you put all the ones on the right, first entry in the product will be the sum of the first row. And for a typical matrix, that would be different.
It's going to community with everything, not just.
But here you see what's the entry that goes in the top? Well, it's just A times that. What's the entry that goes in the second element in the first column? It's just, so second row, first column is B times that. But that's all exactly the same when you put that diagonal matrix on the other side. Yeah. So yeah, matrices don't commute, but some of them do. Some of the nice ones, especially chosen ones do. Okay. Okay, that's a good detour. Okay, first Sylow theorem. Oh, and then he does a quick example. So I think we'll just talk through the proof on the page. I think we can understand it. Because I probably don't have time to write it out. But so like he does a quick example looking at A5. A5 is size half of factorial of 5. Factorial of 5 is 120. So A5 is size 60. Look at the prime factorization of it. 2 squared, 3, 5. So we immediately now know A5 has subgroups of order 2, 3, and 5. Okay.
Not that they do. They have to.
They have to,
It
yeah.
does have subgroups of size 2, 3, and 5. We've just proved that with Cauchy's theorem.
Yeah.
They must exist.
Those are their primes.
Lagrange's theorem allows them, they don't violate Lagrange's theorem, but Lagrange's theorem doesn't give you anything positive about the existence. It just limits the possibilities for 2 combinations of those primes. But now we have something positive. Say A5 does have subsize 2, 3, and 5. I mean, we can find them by inspecting what the permutations are and building them ourselves.
But it doesn't necessarily have sizes 12 and 30.
Not necessarily. Yeah.
Also, does it not tell us how many of each there are?
It doesn't tell us yet. Yeah.
It tells you that there is at least
there's
one.
one. Yeah. But the later side of theorems will give us more information. Yeah. But so the first Sylow theorem extends Cauchy, squeezes some more out of it. Okay. Essentially the similar argument, again built from the class equation, but it gets a bit more. It says, so Cauchy's theorem is basically the first Sylow theorem when R equals 1. First Sylow theorem talks about any power of a prime. So in particular, it'll assert the existence of subgroups of size 4 of A5. Okay, so the first Sylow theorem says you've got your finite group, there'll be primes dividing the order of G, unless G is just a trivial group, in which case, story over, can all go home. But so when P to the R divides G, then G has a subgroup of that size. Okay. We already know this for abelian groups, as the fundamental theorem of finite abelian groups. We can get all of these results for abelian groups just out of that. So it's interesting here to think that this is a non-abelian. But the class equation is good. The class equation allows us to see some of the abelian stuff in G, and then various conjugacy classes. So again, it's induction on the order of G. But I won't write out all the steps. Let's just read through this together. So again, it's induction on the size of G. So quite a similar plan of attack. So because we're going for higher exponents, you see, just glancing down at the end, you'll see a bit of reference to the factor groups. So a base case of induction, smallest interesting case is when the size of G is just the prime P. So how many P to the R's can divide G? What's the possibilities for R? Just one, yeah, because it's only P. Yeah, so again, it's just trivially true. G is the subgroup of itself, of size P to the R. As we're restricted to R equals 1, the size of G is simply P. There aren't any higher powers of P dividing. So base case is okay. So now, okay, we call N the size of G. So we assume it's true. And we assume it's true for all groups of size less than N, where P divides, I think that sentence is wrongly phrased. Suppose that the order of G is n, and that the theorem is true for all groups of order less than n, where P divides, I think what he means to say there is P divides the size of that group. Yeah. That's what he means there. So we're going for the class equation once again. Again, here, okay, he slightly prevents it in a slightly different way, but basically, suppose P to the R does divide one of these. Or the way he's phrasing it, yeah. So the way he phrases, remember, each of these is the quotient, size of G divided by size of the centralizer. If one of them is not divisible, if one of these guys is not divisible by P, that means the full power of P must divide that centralizer, size of that centralizer. Okay. So now, this is a smaller group than G. It's divisible by P to the R. Therefore, it's covered by the induction assumption. So this C of xi has a subgroup of size P to the R. But that'll be a subgroup of G as well. C of xi is a subgroup of G. Okay. So that's your case one in like case two, which is the same as not case one. That's important too, that they're exhaustive. So if this isn't the case, it means none of the centralizers are divisible by the full power of P to the R. You have to argue carefully here. Some of them, they could all be divisible by smaller powers of P. Remember, P to the R is the power that we're talking about that divides the size of G. Maybe some of the centralizers might be divisible by smaller powers of P. But case two, we're assuming that none of them are divisible by the full P to the R. Okay. But in that case, we know that P on its own must divide all of these terms in the class equation. Okay. Because remember, all of these terms are order of G divided by order of C xi. Okay. So we're assuming P to the R divides G. And now in case two, we're assuming that it isn't the case that P to the R divides this. So there must be at least one factor of P left behind in the numerator. Okay, the numerator has at least R factors of P. The numerator has at least R factors of P. And in case two, we're assuming that none of the denominators are divisible by P to the R. So there's at least one P left in each numerator. Okay? Left behind in the whole ratio. So that means each of these terms is divisible by P. Can't say P to the R, but just P. The left-hand side is divisible by P. Therefore, the size of the center is divisible by P. Okay. So if the size of the center is divisible by P, then by applying Cauchy's theorem or fundamental theorem of finite abelian groups, we know the center has elements of order P, subgroup of order P, but it has elements of order P. And now we introduce factor groups. And remember, factor groups are always a good way of passing to a smaller group, a simplified view of the group G. Smaller, because you're quotienting out by a normal subgroup. Okay. So we have this special element G in the center, which we now know the order of G is P. So he lets N be the subgroup generated by G. Now this is a subgroup of the center. Therefore, everything in here commutes with everything else. So that means we can say for every H in G, Hn is equal to Nh. Yeah, because everything in the center commutes with everything in the group. So a left coset, taking any representative from the large group, a left coset is always the same as the right coset.
because indeed, much more than that, it's true that h times a little n is always n times little h. That's true for every n in n, which is this order p. So i.e. n is normal in G. So we can legitimately speak of the factor group G to the n. How big is the factor group? Yeah, size of G divided by size of n. So size of G divided by p. So in particular, it's smaller. It's strictly smaller than the size of G. What power of p do we know divides the size of the factor group? So we assumed at the start p to the r divides the size of G. We've gotten rid of one of the factors of p. So we know p to the r minus 1 divides the size of the factor group. Okay. So it's a smaller group. The induction hypothesis was quite strong. The induction hypothesis said the theorem is true for all groups of order less than n. N is the size of G. Well, here we are now looking at a group which is size strictly smaller than G. And here's a power of a prime dividing it. Okay. So let's pick up where everybody talks then. Consider the factor group of order G over P. By the induction hypothesis, the factor group contains a subgroup of that size, P to the R minus 1. So within the factor group, which is G mod N, there is a subgroup of H, and the size of H is P to the R minus 1. But we want to draw conclusions about G back here. There's the canonical homomorphism from a group to its factor group that sends an element x to the coset xn. This homomorphism is many to one. How many different elements does it send to the same coset? Well, there's always n different elements. N is, yeah. Any element from this left coset gets mapped by the canonical homomorphism to that left coset. So this mapping is not 1-to-1. Phi is p to 1. Right, so every element in here comes from 1 to p different elements here. Okay, under the canonical homomorphism. Each element from here within H, when you pull it back into G and look at phi inverse of H. When we're studying homomorphisms, the inverse image, the pullback of a subgroup is always a subgroup. Yeah. So the inverse image of this subgroup in the factor group is a subgroup of G. How big is it?
So H is PR to the minus 1. The inverse phi of H would be PR.
There you are. So the size of this is p to the r, because all the elements go p to 1 for each one. So each element here generates p elements here. So you got p times the number of elements here. So that's p to the r minus 1. So p to the r. So that's our subgroup of size G. Oh, that's our subgroup of G, which has the required size. As the inverse, okay, he finishes it off rather abruptly there, but the inverse image of H under the canonical homomorphism phi, so that's the phi inverse H, is a subgroup of order p to the r of G. He's running quickly through a few details there, skipping over a few details there. You might want to see that as a little detail to fill in. The canonical homomorphism is always the size of the group you're factoring out to 1. Every element in here has that many inverse images. Okay. But again, that's
that factor group construction is really nicely what allowed us to use the induction assumption. So we were able to pass to a smaller group. It's a simplified view of G, strongly related to G. It had a subgroup that did a certain nice job in the direction of the Sylow theorem. When we mapped it back, it was the subgroup that did the job for the Sylow theorem in G. So that proves the first Sylow theorem. Just to recap, it's an induction proof, base case, trivial, assume it for all groups of smaller size, and then an exhaustive case one and not case one. So case two is the kind of tougher argument. It required passing to the factor groups. And it shows the power of the factor group idea in enabling us to prove these things. So we'll do some exercises on Friday. We'll look at some of the consequences of this. So we now know that A5 does have a group of size 4. Because 2 squared divides 6. Okay. So you better finish there.
5 to 3. Well, we'll have a look